Our first speaker today is Dr. Dan Moore. He is from the University of Toronto, and he's going to be speaking about one of my favorite topics, protein. So we're going to let Dan start because he has to get to a hockey game with his kids. So Dan, take it away. And again, I ask the audience to mute your microphone so it doesn't mess up Dan's talk. Okay, Dan, take it away.
Great. Thanks for the introduction, Jose, and the opportunity to speak to. And bit of a cliche, I do have to run to the rink. Being Canadian, this is the prime time season. So today I'm going to talk a little bit about some of the protein work that we and others have done, and focus on recommendations that we can use to optimize the remodeling and of skeletal muscle primarily, which ultimately will help athletes recover from and adapt to the stress of exercise. Slides. Just a couple of acknowledgements here. These are the people that get to do the work and some of the funding sources that support some of my research, none of which have conflicts with the material I'll talk about today. So important for all athletes is to have an adequate quantity and quality of lean mass, especially of skeletal muscle mass, which contributes about 40% of the total body mass. And in order to optimize this, we have to appreciate that this tissue is very dynamic. So it's constantly turning over as we see. So old or damaged or misused proteins are targeted for degradation, and they're broken down into their constituent amino acids here. And these amino acids can leave the muscle. So the muscle is the only place that we can store amino acids in our body, and used for other processes such as the formation of glucose or supporting other vital organs. They can also be used as an energy source. In that case, if we use these as energy, then we have to replace them through the diet, especially the essential amino acids that our bodies cannot make. But ultimately, what we want to do is find ways to optimize the reutilization of these amino acids into building new muscle proteins. And so this turnover allows the muscle to adapt to the stress of exercise. And the difference between synthesis and breakdown determines whether or not a muscle is gaining or losing mass. And so this turnover occurs throughout the day, and exercise is a potent stimulus of increasing this turnover. So what I'm going to talk to you today, I want to highlight that when we talk about protein, we like to focus on how much we should consume in a single meal, because that's going to influence the metabolic processes that occur in skeletal muscle. And really to highlight that we can support this remodeling of muscle and adaptation through a range of different types of dietary protein choices. And I'd like to also highlight some of the work that we and others have done in the space of endurance athletes to convince you that protein is not just for building bigger muscles. And then hopefully I'd like to take it home at the end and convince you that protein targets and recommendations for these should not be overly complex. So if we look at what happens throughout the day, so here we have kind of a schematic of changes in muscle protein synthesis, the solid line, and muscle protein breakdown, the dashed line. So if we wake up in the morning or for more than about 4 to 5 hours removed from our last meal, we're in a negative balance. So the difference between synthesis and breakdown is higher than synthesis. And so when we consume a meal, the protein in the meal, or the amino acids that the protein provides, are the stimulus for increasing protein synthesis, and the insulin response that we get through protein, but also some of the other macronutrients, will help suppress protein breakdown. And so if we don't exercise, these fed state gains counterbalance the fasted state losses, so our muscle mass is relatively consistent. Now, if we want to find ways to gain muscle mass, we have to enhance that positive net protein balance, and that's done through primarily the performance of resistance exercise. And so we have a potent stimulus in protein synthesis that is augmented by a protein containing meal. And the change in breakdown is a little bit attenuated. But what happens is those fed state gains are greater than those fasted state losses. So over time, with every meal that we consume, we gain a little bit more protein. And over time, we can see that translates into bigger and oftentimes stronger muscle. So some of the earlier work that we and others have done identified 20 grams as a protein intake that maximizes protein synthesis. And you may have seen this or heard about this in some of your reading, or a lot of protein supplements target this as at a minimum level. But we feel like this is perhaps can be a bit misleading if you have a larger or a smaller athlete. Then maybe we need to tailor it according to body mass. And so this is some of the work that we've done, looking back at studies that have measured changes in myofibrillar protein synthesis. So FSR is just another term for synthesis. And the myofibrillar proteins, if you remember, are the contractile proteins. So actin, myosin, about 65% of the muscle protein is contained in the myofibrillar, and these are the ones that are going to help our muscle hypertrophy and generate the strength that many athletes need for performance. So if we look at all the studies that measured changes in protein synthesis compared to a protein intake, and we can normalize that to body mass to make it a little bit more translatable across different body sizes, we see that there is a dose response. So the more protein you consume, the greater the increase in protein synthesis. And we see that there's an inflection point that lines up roughly with about 0.3 grams per kilogram. So this is whey protein. If we target this as a relative dose in a given meal, then it will be the point at which we'll likely optimize or enhance, maximize muscle protein synthesis. And certainly we can consume more than this as a target. And the studies that did this actually showed that markers of amino acid oxidation, or urea production, which are both scale with higher protein intakes, since the way our body disposes of these excess amino acids, there's a linear increase. So if we want to find ways that we can optimize or be most efficient with our protein, then 0.3 grams per kilogram would maximize synthesis and minimize oxidation. And just as a comparison, we can look at what happens at rest, and rest is a little bit more muted than exercise, but seems to plateau at around the same point. And studies have followed this up and showed that whether you have a high or a low lean body mass, as long as you're doing whole body resistance exercise, this protein dose would remain consistent. Now, a lot of the studies that have looked at this have used animal-based proteins, and specifically whey, which many of you know of as being quite an anabolic protein. It's indicated here. So all the gray bars are animal-based, and all the white are plant-based. And so you can see whey is not only high in the essential amino acids that our bodies can't make, but also in leucine, which also helps turn on the process of synthesis. And if you look across the board compared to what our muscle composition of amino acids are in the black bar, you can see that animal-based proteins are typically a higher quality. They have a higher quantity of the essentials and a greater ratio. And so some plant-based might be deficient in one or more essential amino acids. So we have to consider this when we look at types of protein we should consume. And so if we look at protein intakes below this threshold, I think there's scope for looking at animal-based or leucine-enriched proteins as being more efficient at turning on this process. But once you exceed this, then certainly plant-based can be a source that can support optimal muscle remodeling. And just as an example, these are just some studies I pulled from Luc van Loon's lab in Holland. And they compared different plant-based proteins compared to milk or milk protein concentrate. And so you can see here there's potato, there's a blend of peas and wheat and corn, cheese, and this is not rice. Those are mealworms. So insects can also provide protein and essential amino acids. And you see that when the dose of protein that these individuals are consuming after exercise is greater than the 0.3 grams per kilogram, it really doesn't matter what you're consuming. So you can make a suboptimal protein better by just consuming more of it. And so the 0.3 grams should be qualified when we talk about what is it we're actually consuming. There's some evidence that suggests that if we can space our meals out throughout the day, we may be more efficient at using those amino acids for building muscle protein and not diverting it to oxidation. And this is just data that looks at, these are actually Dutch elite athletes, and their distribution of protein throughout the day. And you can see that as with whether you see this in North America or Europe, many more Western-based societies have a skewed pattern. So we eat far more of our protein later in the day. And if this is the threshold that will maximally turn on synthesis, then we may be exceeding it and leading to oxidation in the evening, and maybe not reaching it in a breakfast meal or certainly in snacks. There's still some research that needs to be done that's suggesting looking at time restricted feeding. I know this is a common approach for some types of athletes. And so we don't know where that's at, but certainly past work that we've done, spacing 4 to 5 meals out throughout the day at around that 0.3 grams per kilogram was greater than consuming smaller meals or 3 larger ones at supporting muscle protein synthesis during recovery from exercise. So we can do some simple math and look at 4 to 5 square meals every 3 to 4 hours, and we get to an intake of about 1.2 to 1.5, which in theory would support muscle protein synthesis and lean mass gains with training. And so what does that look like? Well, this is some data from Stu Phillips, Matt Kinprof, for those of you who follow him on Twitter or X. And they looked at a meta-analysis at changes in fat-free mass with resistance exercise training, normalizing the protein intake per grams per kilogram. And so they saw that there was this dose response, and about 1.6 grams per kilogram seemed to be where they maxed out the gains in fat-free mass. So certainly you can consume more, but those who want to be efficient, maybe 1.6 would support that. But once again, looking at these gains in fat-free mass, you might have individuals consuming less than that target and substantially more and still gaining the same relative fat-free mass. And so we wanted to probe, well, how is this possible? And so we studied the change in whole body protein balance as a surrogate for lean mass gains in athletes who were habitually consuming 2.2 grams per kilogram per day. And so you can see those athletes had a net balance at about 12.5, and the units aren't important here, but the relative differences are. And when we switch those to a moderate intake, or 1.2 grams per kilogram, you see that their net balance was attenuated. And this is likely because if you chronically consume a high protein diet, your body gets very good at using that as an energy source. And so when you switch down to a lower intake, you need to adapt those pathways that burn protein as a fuel to help turn those off. And so what we saw is if we followed them out 3 to 5 days, you saw the net balance started to creep back up. So we can certainly support positive whole body protein balance with resistance exercise over a range of intakes, but being mindful that if you switch from a high to low, it's going to take time for your body to adapt. If we look at some of the additional work from Stu's lab, looking at changes in strength, and this is bench press and leg press. This is a meta-analysis as well. And I've just highlighted here that 1.6 grams per kilogram, which may optimize lean mass gains. You see that there's really no difference. That line is flat, suggesting that over a range of intakes, there doesn't seem to be a substantial difference in strength gains due to higher protein. There may be other factors associated with this, but on balance, this suggests that protein intake may not be the primary determinant. And you can look at leg press and say there's a trending line upwards. And so if you're an athlete that wants to get everything they can out of their training, you might self-select a higher intake. But this, I think, shows that you can certainly get bigger and stronger on moderate protein intakes throughout the day. So what I've just told you is that turning on protein synthesis in the muscle after exercise is a form that is essential for recovering from and adapting to exercise. We can optimize this or be efficient with our protein intake by targeting 0.3 grams per kilogram per meal, and spacing this out throughout the day theoretically would be the most efficient way to eat. But in the end, we can certainly support adaptations to training across a range of intakes, and certainly more than the RDA, which I would imagine many people, especially with their training, would be far exceeding that anyways. So if we now switch into endurance exercise, it can be quite a bit of a stress on the body. And so one of the biggest stresses is that we use protein as an energy source during our exercise. We can't shut that off. Maybe up to 5% will be burned. We do favor carbohydrate and fat, but we will burn protein as an energy source. And once we do this, we have to replace it through the diet. A lot of exercise, especially which is weight bearing, can induce stress on the muscle and cause some minor protein breakdown, which has to be repaired. And there's some evidence that we might damage some of the proteins in our gut through the ischemia we might get when we train. So what does this have? What effects does this have on the requirement for protein after exercise? This is data from Luc Van Loon's lab, Tyler Church-Robinett, the first author, and he looked at changes in, this is once again the contractile proteins, the myofibrillar proteins. We need to make sure that those are optimal to have a high power output, regardless of what type of athlete you are. And immediately after 90 minutes of cycling, they saw that upwards of about 0.49 grams per kilogram was needed to turn on or maximally stimulate the resynthesis and recovery of this protein fraction. So if you compare that to resistance exercise, you see it's actually a little bit greater with endurance exercise, and the difference being about roughly 15 grams of protein. And if you do some of the math, that actually aligns quite nice with how much protein they would have burned as energy during this type of exercise. So a lot of this post-exercise increased requirement with endurance exercise is to replenish the protein we use as a source of fuel. We can also look at some of the other proteins in the muscle that would be important for adaptation with endurance exercise, and this is the synthesis of mitochondrial proteins. And there might be a slight trend, but there's no real difference. So we don't seem to require extra protein to support the remodeling of this important organelle. But this is the amount of the protein that they consume that actually ended up in the mitochondrial protein. So if we eat protein, it can still be a building block for those mitochondrial proteins. If we look at how often endurance athletes consume protein or consume, meals, to meet their energy requirements, they're often eating greater than 5 meals per day. And so if we do some simple math, and we say the post-exercise meals should be 0.5 grams per kilogram, and then the meals thereafter, 4 of them would be 0.3 grams per kilogram, we see that their requirement might be as much as, or maybe even slightly more than resistance exercise athletes at 1.7 grams per kilogram per day. So we wanted to test this in a model, and this is a little bit deep, but I'll just introduce you. It's the indicator amino acid oxidation. Is based off the fact that we can give amino acids that have a carbon that's slightly heavier than those that are normally found in your body. And what that means is when it's used as an energy source, we can pick it up in the breath. And so the important point here is that we have 2 fates of amino acids that we eat. We can use them for protein synthesis, or we can use them as energy. And so the only way that we can use our indicator for synthesis is if we give the other amino acids. And so just to orient you to the data that we're going to see here, as we give more amino acids or more protein, we burn less of our indicator, which is the reciprocal of whole body protein synthesis. So when we get to this break point in our model, it's what would be required to maximize whole body protein synthesis, which is important, we believe, for supporting adaptation to endurance exercise. And so these are some data in males and females who were performing 35 kilometers of running, including 20 kilometers on the day that we measured them, and training, and we measured the females in the luteal phase. And what we saw was that these are the break points, but if I'll just overlay protein synthesis, what we saw is the requirement for protein was identical between males and females. And we like this because females are relatively understudied in this field, but also the requirements do not seem to be much different than males. So some of the historical work done only in males may be able to be translated to females as well. And I just put this hash line here because this is also what we measured in male athletes in a very controlled laboratory setting. And this study was done in the field of research. And this is where they would be at if they didn't do exercise. So the requirement is substantially more in endurance trained athletes. And if we look at what that means for protein, for performance, we extended our study over 4 days. And so here are the mileages that they did on each of the 4 days. And I apologize, this should actually be 20 kilometers, not 10. And we fed a range of protein intakes. So our optimal was the high, a moderate was the lower boundary that the ACSM is currently recommending. And this is a little bit more than the RDA. Protein balance is less important for the athlete because it doesn't mean much. What they actually look for is performance. And so when we looked at the change in performance over just 4 days of training, consuming an adequate energy, high carbohydrate diet, that we only changed the protein intake, we saw that the athletes that were on the optimal, which is called high, they actually got a little bit faster. And those that were on the moderate or low got slower. And so this is only 4 days. The statistics didn't bear out, but the trends aligned with what we see as being optimal for these athletes. And we also measured their strength, and we saw that those on the higher intake got stronger in 4 days of training, and those that didn't got weaker. So we think this is nice proof of principle that what we measure in the lab for metabolism has direct relevance to what the athletes really care about, and that is, do I get faster? Do I get stronger? So what I've just told you with endurance exercise is that right after exercise, depending on how long they've been exercising, they may need to consume a greater meal protein intake to replenish the protein that they burn during exercise. But throughout the day, they can still target that 0.3 grams per kilogram. And that 1.8 grams that we saw is sufficient for their energy or for their protein needs is really still a relatively low amount of energy as protein. So as long as these athletes consume adequate energy, they're going to more than meet the protein intake. And so just to summarize everything that I've just said, when we look at athletes, the first thing they need to do is train hard. The second thing is to consume adequate energy, because oftentimes this means that the protein intake will also follow. Figure out whether you're a 4 or 5 meal a day, divide that up, and take a food first approach. There's certainly an opportunity for supplements for convenience, or if you're trying to increase the intake of certain amino acids, but food first matters most. So I thank you for your time, and I'll let Jose let me know if I have any time for questions.
Yeah, if anyone has any questions for Dr. Moore, you could just post it on the chat. I just wanted to make sure for our audience, when you're comparing endurance versus strength power athletes, what would the practical post-exercise recommendations for protein intake be?
For strength athletes, I think we're still at the 0.3 grams of protein per kilogram per meal. But then the endurance athletes are going to need a little bit more than that. And you know, what is an endurance athlete? How much training? We're still not quite there. We did a 20-kilometer run was what they were recovering from in our lab, but appreciating that some athletes might do more or less than that. So I think if you do more than that, then I think proportionally you're going to need a little bit more protein to replenish what you use as fuel. And if you do less than that, like myself, when I go for runs with the dog, I don't worry about the protein at all. It's just about eating a meal, in close proximity to when I finish the exercise.
Now, another common question as it relates to protein is, I mean, I know a lot of guys. In fact, I think Dr. Willoughby is one of those guys that easily consume 60 to 100 grams of protein in a single meal. And the question often is, well, it seems like muscle protein synthesis seems to, I guess, peak or plateau at about 40 grams, roughly. So what are your thoughts in terms of how Dr. Willoughby eats? Because clearly he can eat like a small cow per meal.
Yeah, and I think this is just the power of the human body. We can certainly eat a lot of protein, and I'm not demonizing large intakes. That's a personal choice. But at some point, there is going to be a maximal amount that can be deposited in body, and especially muscle protein. So it's likely that we're just converting that into urea and glucose, and we're using that as energy. But I know some athletes, and I work with others that want to get everything they can out of their training. And the studies that we've done, we still see an upward trend beyond 40 grams. So the athlete that wants to push out that extra 3 to 4% recovery, I would still recommend that it's not an issue as long as their kidney function is fine and they're adequately hydrated. Certainly, we can consume a lot of protein, and I do as well. On occasion, we just had Canadian Thanksgiving here last weekend, and I certainly gave my kidneys a workout there.
All right, one last question for Dan. Has there been any recent data on how to mitigate the negative effects on endurance training on the gut? Not something I'm familiar with, but perhaps you could address that.
Yeah, so could yeah, we're pushing outside of the comfort zone here, but certainly high volumes or intensity of training can lead to gut damage or leaky gut, which might predispose people to illness. There's not a lot that we can do to get around that, to be honest. I'm not aware of any research that's finding ways to mitigate that. But the other aspect of the gut health is athletes who consume carbohydrate during exercise. They might not be able to absorb it all, so that can cause GI distress. We're seeing that maybe you can adapt to high carbohydrate intakes if you consistently train like that. But certainly, that's something that is a concern, and it's not my area of expertise, but I don't see any data suggest that protein during exercise or immediately after can ameliorate any of those symptoms associated with leaky gut.
Awesome. Well, Dr. Moore, appreciate you coming on and edifying us on protein, and please do enjoy the rest of the day with your kids and hockey. So again, thank you so much.
All right, thanks again. Thank you, everyone.